All right, so I just double confirm to make sure that the recording is on and also it is recording the voice. So that's good. We'll check it occasionally because there are times where I have strange technical difficulties where it was record halfway and then it stops recording. So we'll check on it occasionally. All right, so I'm hoping that most of you have completed your interactive teacher-learner agreement thing, which is the syllabus. So for the most part, it's really just for you to read the material and just kind of sign it off and say, yes, I acknowledge that I know where to find this stuff and I understand it, okay? It's kind of long, I know, so you can kind of skim through the most important part and ignore some parts where it's just a suggestions or recommendations or stuff along that line. So what we'll do today is to continue our discussion on numbers and data and number representation. But today we'll get into adding numbers, okay? Just to make sure that we have a continuity from last time. Last time we talked about transistors, okay? But transistors are nothing more than switches, valves of sorts, okay? The significance of transistors and relays and vacuum tubes and stuff like that is you are using electricity to control the flow of electricity. Okay, and that's how you can stack or have a network of these devices to make computers. Are there any questions about that part? Let me just kind of bring up the notes first so you know what I'm talking about. I also fixed a few things in my notes. The naming of the conjunction and the disjunction is now fixed. It is now correct. So I'm going to fast forward, through this stuff until we get to this slide. And this is a simple network of transistors, 2 p-channel transistors and 2 n-channel Mosfets. And this is, how you can make a simple, what we call a Nand gate, which is negated and or negated conjunction gate. Are there any questions about this? Okay, no questions? All right. So what you can do, instead of looking at this as a circuit diagram with T1 and T2 as the quote-unquote input and T3 as the output, one thing you can do is to look at this, and instead of looking at this as a circuit, let's go ahead and take a look at the logical expression. Oh, actually I got it from last time already. This is the logical expression that is expressing exactly the same thing, except in this time I'm using the C++ logical operators. The exclamation point and the ampersand are both logical operators. Are there any questions? No questions?
Can you go over the schematic a little bit, like one more time?
The schematic?
Yeah.
Well, the schematic has Q1 is this transistor, Q2 is this transistor.
Okay.
Q3 is this one, and then Q4 is the last one. Okay? And the properties of the n-channel MOSFET, which are Q3 and Q4, is they turn on, they completely connect the circuit when the input voltage to the gate is high.
Okay.
The gate is this connection here.
Okay.
Okay? And then for p-channel MOSFETs, the gate is on these two lines, but the p-channel MOSFET turns on when the input voltage is low, not high.
Okay.
So that's the main properties. You basically have two types of transistors, and each one turns on based on the flip side of the voltage of the other one. And that's how it works, because when T1 is high and T2 is low, then what T1 is going to do, since it's high, is going to turn off this transistor.
Okay.
But it will turn on Q3. Okay? And then T2 is going to turn, because it's low, it's going to turn on Q2. Now, if you turn on Q2, T3 now has a path to go to VCC, which is a high voltage. Okay? But T2 is going to turn off Q4 because it has a low voltage. So this transistor is not connecting, even though Q3 is connecting, but because Q3 and Q4 are connected in series, they both have to be on in order to have a connection to ground. So T3 ends up not having a path to ground, but does have one path to VCC, and as a result, T3 becomes a high voltage.
Okay.
But that's just one example. Okay, the entire truth table is presented in the slide. Okay. is this a complicated circuit? What do you think? 4 transistors. Okay, it's not complicated at all. But the significance of this slide is to illustrate we can now go from transistors, which are very basic, simple semiconductor devices, to what we call gates. Now, what is a logic gate? A logic gate, as I have illustrated on the other side, is basically just a logical operation. Okay, so instead of expressing the logical operation as an expression in C++, I'm now expressing it as a simple circuit, making use of transistors. Are we doing okay so far with the connection from devices like transistors to a higher level construct like the logic gate? Is that part okay? All right, cool. All right. So the next thing that we talked about the other day, and I know the font is really small, but that's kind of okay for now because I just want to show you the diagram. So the other thing that we talked about is, okay, this is a kind of weird little construct. It's called a negated AND gate. So why not a regular AND or regular NOT or OR? Well, we can make all of those things out of a NAND gate. To make a NOT gate, we just have a NAND gate here. We connect X1 or the input port to both of the inputs, and then the output goes to the output port. Okay, so this way we're only using 2 rows of the truth table, because when both inputs are exactly the same, then we are using the first row or the last row, where the inputs are either high, both, or low, in both cases. But in both cases, what they do is they negate the input. Because on the first row, when the input is high or 1, the output is low, which is a 0. On the last row, when the input is low on both inputs, the output is high, which is exactly the opposite. So it acts as a negation gate. Are there any questions about the negation part? Yep, go ahead.
Maybe not the negation part, but this truth table is a representation of your diagram.
The truth table is representing the behavior of this diagram, of the actual circuit itself. But we look at the entire circuit and go like, well, instead of looking at the circuit with the individual transistors as components, we just use a simplified symbol, which is this symbol here. This is an AND gate. But when you add a bubble to the output, it becomes a NAND gate because the bubble negates. So we call this a NAND 2 because it has 2 inputs and 1 output. Okay? And we'll get to these terminology and also the diagram later on when we actually play with a logic sim, which is a really useful tool for learning this stuff.
Yeah, I had a question about that when you get to it. So.
Okay, sure. We will get to that. So we took care of the negation gate, and this one here is a disjunction. Now, disjunction looks really, really complicated. It requires 3 NAND 2 gates in order to do disjunction. Okay. In other words, we're implementing disjunction or the 2 vertical bars in C++ using 3 NAND gates. The way it works is the equation. So when you look at the equation, the little V symbol is an OR, the little wedge symbol is the AND, and then the little cliff symbol here is negation. So the way it works is we take A or B, okay, and then we say, well, double negation cancels the entire thing, so that's why we can establish the second expression. Are there any questions about going from the first to the second expression? I think at this point, all of you should know, not is the same as doing nothing. Okay. The magic is going from the second one to the third one. In other words, we take this part, which is having a NOT on the outside of an OR, and we convert it into this part here, which is distributing the negation to the components, but turning the OR into an AND. That is called De Morgan's law. Okay? De Morgan's law establishes that these 2 expressions are equivalent. They're exactly the same thing. We will encounter De Morgan's law later as well. So at this point, I'm just saying, okay, this is how the equation is derived. But once we get to the third form, we now have all the things that we need in order to implement it using just NAND 2 gates. The first thing is, well, what about A? We need to negate A. But we know how to do that already from the previous construct. So that's why we have this part here, which is the negating A, and we have this part here, which is negating B. Once we have negation of A and negation of B, then we have a negation, we have a conjunction here and a negation on the outside. Well, how do we do that? Well, that's an AND, right? Because we have a conjunction and a negation on the outside. So that's why we have a third NAND gate here, taking the not A, the not B, and them together, and then negate the output, and that becomes OR. Okay? So this would be a good time to kind of show you, well, I don't really believe that, okay? You know, show me that this actually works the way it's supposed to, using Logic Sim, okay? So this is a perfect opportunity to get into that part. So I'm gonna start up Logic Sim, and I have it downloaded already, I think. Maybe in my downloads folder, or maybe not. No, I do. Okay, it's Logic Sim Generic 2.7.1, okay? To start this one, you just have to, I just do it using the command line. In Windows, you can probably just double click on the jar file and it will open it up correctly, assuming you have a Java Runtime Environment, JRE, installed already. And in Linux, you know, it's just one extra step, you have to type the command. There we go. So this is Logic Sim. It's a pretty nifty little tool, okay? It's really, really nifty. So what we'll do is we'll design the circuit of a regular OR using that mess of NAND 2 gates, and then we'll do it with just a regular OR gate. And it will feed input into both constructs, and then we'll look at the output of both constructs and see whether they are truly equivalent, okay? So here we go. We can magnify first. The zoom control is down here at the bottom. So we'll just go ahead and kind of zoom in a little bit because this way it's easier for me to see the whole thing. You can see all the common gates already here, or you can go to the gates category and then pick what you want. So we can now say, okay, well, let's go ahead and use some NAND gates. And the default, has 3 inputs and is a pretty big, design. You can change all that. You can change it by changing it has 5 inputs. We don't need 5 inputs. We just want 2 inputs. And with 2 inputs, this is way too big. It takes up a lot of screen space. So we'll go ahead and change that from a medium size of gate to a narrow size. That really is just controlling how much space it takes up. It doesn't change anything in logic. All right. So now we have 1, and since we already know that we need 3 of these things, we'll just do a Control-C and paste one more time. So now we have all the gates ready. Okay. Are there any questions about these steps? No questions? All right. Next, we need some terminals. Now, there are 2 types of terminals. This one is a pin, or it's called a pin, but it's the same thing as a T1, T2, and T3. T1 and T2 are input pins, and input pins are the ones with a square. Okay, so we'll go ahead and click this. So we can add 2 input pins. So one can go here, and then the other one can go here. Okay. We have 1 output pin. So this output pin is going to go here. Okay. So now we have all the basic stuff that we need in order to implement a OR, but using a NAND 2 gates topology. So now it's time to make the connections. It's easy. Drag and drop. So you just drag from a terminal, and you can stop a little bit if you need to make a turn, and continue to drag to finish the circuit. Like so. Now obviously in this case, I could have done each individually first, and then I do a copy and paste, so I don't have to replicate the process. There we go. Wow, they're actually symmetric. Okay, so now we have a quote-unquote OR gate. Okay, but it's made out of 3 individual NAND 2 gates. We can test this a little bit first. Okay, let's go ahead and test this. When you're testing something, you want to switch to the simulation mode, and we'll just go switch to the simulation mode where you can click on each one and it changes the value. And this is simulating the circuit already. You can see 0 or 0 is 0. 1 or 0 is 1. 1 or 1 is 1. 0 or 1 is 1. And I think that should be, that's it, right? That's all the combinations. We did a 0 or 0 already. So it does work. But if you don't think, oh, but I'm not really 100% sure this is actually working, let's go ahead and just get a regular OR gate and try that out. Same thing, okay? We can change the size to narrow and change the number of inputs to just 2 because we only have those 2 pins. And this time I can, well, okay, I have to drag this one over a little bit so I have enough space to bring the wires down. So what we want to do this time is to drag from here to here. And you can see, using when there is an actual connection at a junction, there's a little dot to denote that they're actually connected. When there's no dot, it means those 2 wires are just flying over each other. There's no actual connection. Okay? And then we'll do the other one with this guy. And it will need its own output pin because otherwise, if the output do not agree, then we'll have a problem. All right. So now we have a second circuit using just a regular OR, and those 2 output pins, the one coming from the 3 NAND 2 gates and the one coming out of a regular OR gate, they should agree all the time, right? So now we'll go back to simulation mode and check. 0 or 0 is 0 in both cases. 1 or 0 is 1 in both cases. 1 or 1 is 1 in both cases. 0 or 1 is 1 in both cases. I have just tested all possible input combinations for a circuit that takes 2 Boolean inputs. And if the output is identical for all 4 possible cases, they are truly equivalent. That's the proof. Are there any questions about this little circuit here or how to use logic sim? Go ahead.
Are the OR gates more complicated internally?
Well, internally they do not have OR gates, or it depends on the device, okay? But a NAND 2 device is actually pretty easy to make out of transistors. Okay. Alrighty, so now we can go back to our web page. A non-negated conjunction is easy because you just take the output of a NAND 2 and negate the output itself, then it becomes a non-negated conjunction. All right. Analog versus digital. In theory, the control signal to a transistor is continuous. In other words, the voltage that you're feeding to the gate, let me just scroll back a little bit here. The voltage that you apply to the gate of a transistor does not really have to be 0 or 5 volts or 0 and 1.8 volts. It can be anywhere in between. You can control these valves so they're partially on. Okay, that's entirely possible. But why don't we make computers that are analog? Why do we have only digital computers? Why do you think that's the case? It is easier, exactly, because if you want to make an analog computer, the pitfall of an analog computer is you have to select your components very carefully, because the transistors, they all have to respond exactly the same way. If I apply 50% of the full voltage, I need the transistors to turn on to the same degree. That is not easy to do. Okay, matching transistors so that their behavior, not at the extremes but in between, are identical, that's not easy to do. And that's partially why stereo equipment or power stereo equipment is expensive, because they have to match the characteristics of transistors. But in computers, in digital computers, we don't have such a problem, because what are the 2 states that we really care about when we are talking about transistors inside a computer?
On or off.
On or off, exactly. Okay, they're not partially on, partially off. So that is the reason why we have digital computers instead of analog computers. So instead of thinking in terms of transistors, which is really low level and a lot of details, for computer scientists and computer engineer people, they want to think in terms of gates because they are more they're higher level constructs, and that's closer, resembles how we think closer. A gate is an atomic unit that performs a logical function. An AND gate performs conjunction, ampersand ampersand. An OR gate does the OR, and so on and so forth. This is entirely optional. If you want to see how the other gates can be done using transistors, you can look at this slide here. It actually is a pretty good slide to read if you are going into computer engineering or electrical engineering. This particular linked document is going to be beneficial regardless. Okay? If you are a computer science person, well, you can kind of ignore this part because it may not be that relevant to what you will be doing or studying. As far as we're concerned, we can just make use of regular AND, OR, and NOT gates. This is because there are software tools to convert and optimize the use of gates and transistors regardless of how gates are specified. In other words, if you design a processor and you make use of all of these other gates, there are quote-unquote compilers that can compile the design in gates and translate everything down to a transistor level. Okay, and optimize the whole thing. So from your perspective, you don't have to think in NAND 2 gates. You can just think in terms of OR, and regular negation gates. Yep, go ahead.
Is it true that NOT AND is the quickest operator to resources-wise?
It depends on how they design the substrate. It also depends on what type of device you're dealing with. So. Do you guys know what is a Fpga or a CPLD? Okay, an Fpga, is a field programmable gate array. Okay, it is kind of like a programmable chip, and you can configure it to implement. Oh, I want this AND gate here, that NOT gate here, and that OR gate here. But underneath is a very uniform type of design. So they will all be like NAND 2 gates, they will all be NOR 2 gates, and whatnot. So with those, you will have to eventually translate everything down to NAND 2, NOR 2, or whatever is native to that design. CPLD is kind of the same thing. CPLD stands for Complex Programmable Logic Device. It's kind of like Fpga, except in Fpga, when power shuts down, the device would lose all the programming. So every time you power up the device, it has to load the configuration from some sort of persistent memory. With CPLD, it is persistent by itself, but it is reprogrammable. It's kind of like a flash technology.
Okay.
So then we talk about representation, because the number of samurai in this picture is a quantity. But then we can use different words, different symbols to represent the quantity. Are we still doing okay so far? Okay. And same thing applies to this face. Okay, we say it's a happy face, but happy is just an English word. If somebody has no exposure to English whatsoever, that word means nothing. Okay, the sound of happy actually is meaningless. So that basically brings us to brought us, because we talked about this already, it brought us to base conversion. Okay? The importance of base conversion in this class is we will be dealing with binary numbers a lot in this class. Okay, so knowing how to do base conversion and the basic principle of base conversion is really, really important. Okay? So one way to look at base conversion is, well, instead of having the denominations of the usual penny, nickel, dime, quarter, dollar bills, and so on and so forth, we'll think in, oh, maybe we'll have dollar bills, $2 bills, $4 bills, $8 bills, and so on one side. On the other side, we'll have half-dollar bills, $quarter-dollar bills, $8 bills, and so on. Can you still come up with the same quantity using that alternate system? That's the question. And from the previous class, I think we can do it. It sounds a little awkward, right? Because that's not how we usually do things, but it is possible nonetheless. What we'll do today is to kind of go over that one more time, but we'll kind of do it a little bit quicker than last time. And I'll just come up with a somewhat random amount here. Bump up the font size because I think it's kind of small right now. It's still kind of small. There we go. Did it get any bigger? I don't think so. All right, so let's go ahead and just look at a number. Let's pick 37 and 75 cents. Okay. All right, so this is the quantity that I want to express, but only using the new system of denomination. Okay, dollar, half dollar on one side, and it will get half each time, and then on the other side we have $2, $4, $8, and it will just double with each one. Okay. Where do we start?
Which side do you want?
Well, that's a good question. Which side do we start with? Do we start with quarters, or do we start with larger denomination, larger bill, the larger ones? Okay. So let's deal with 64s first. Okay. How many 64s do we have?
None.
None. And what is the leftover?
37.75.
The whole thing, right? Okay, cool. How many 32s do we have?
One.
And then the leftover is
575.
575. And do we have any 16s?
Nope.
No 16s, so the leftover is the same as before. How many 8s do we have?
Zero.
None. And we have the same as before. How many 4s do we have?
One.
We can have one, and we have $1.75 left. And after that, how many 2s do we have?
None.
0. So we have 175 left. How many 1s do we have?
One.
Just one. And then we have 75 cents left. How many halves do we have?
One.
1. And we have 25 cents left. How many 25 cents do we have?
One.
1. And then we have 0 left. And we're done. Okay? So you look at this little table and you go like, well, I don't see a binary number. Or do you?
It is.
It's a binary number, right? So the binary number here is reading these numbers vertically. Okay? So this number in binary is 0, 1, 0, 0, 1, 0, 1, 1, 1. But it's not a whole number, is it? Because the quantity that I'm trying to represent is not a whole number. So now the question is, where do I put that dot that separates the 1 from the fractions? How many places from which side?
2 to the right.
2 places from the right-hand side. So the dot should go here. Now it would be improper to call this a decimal point because it is a binary point at this time. Okay. Are there any questions about the base conversion done here? No. Okay. But that's the idea, okay? That really is the idea of base conversion. Knowing how to do base conversion to base 2, do you think you can do it to base 7?
Yes.
It's the same principle, right? The only difference is when you convert to anything other than base 2, you actually have to do division. Because you have to figure out, okay, how many 7s do we have? How many 1s do we have? And you can have 0 up to 6 of each. But in binary numbers, it's 0 or 1. So it only involves comparison. There's no division involved. All right. Any other questions at this point? Yes?
So when we had, after 175,
Uh-huh.
so we went into 1, we subtracted 1, we have left with 0.75.
Right.
And then minus a half should be like 0.70, right?
0.70.
Or am I doing something wrong there?
Minus a
Something
half
goes wrong.
is 0.75 minus 0.5, and the end, the result should be 0.25. I think you're off by 1 decimal place.
Oh, okay.
Yep.
Sorry.
How is the binary presentation of floating point working?
Well, we'll deal with that when we get to floating point numbers. So we'll dedicate, actually about a week or two to deal with floating point numbers. It's actually quite complex in a way. This is not floating point. This is kind of like fixed point because we kind of implicitly know where this point is supposed to go. Okay, but this is really just an exercise, so we know how to do basic base conversion. Any other questions? Okay, if there are no questions, I'm going to pass the roll sheet. If your name does not appear on here, just go ahead and add your name. I met the dean this morning. He just came back, and he said, yeah, we can add all the students because the district is short on students right now. Okay, the way it works is the state would fund the district. They will give the district a certain amount of money, and it will fund X number of students. And this year, for this quarter, for whatever reason, we are not at 100% of the capacity. In other words, let's say the state funded ARC for 90,000 students, okay? We only have 98% of the funded 90,000 students, enrolled. In other words, some of the money that the state has given to the school is not, funding actual students in the classroom. So the state keeps track of these things, and so the next year it will impact, how much money the state is going to fund the community college. So that's why we want to be at 100% capacity all the time. So when we drop below 100% of funded students, the district, kind of get a little anxious and say, oh, we need to do something about it. So I think we just bumped the deficit from 2.17% to 2.16599%. It's going to make a little change. Alrighty. So when this slide is over, we're going to move on to the next one. The next one is going to be a lot of fun. We also have homework assignments, but I'm not going to show you how to do the homework assignment during lecture time. Instead, I'll do it during lab time. That's what lab time is for, okay? So during lab time, I'll show you guys how to do the two quote-unquote lab activities. The first one is using LogicSim, and then the second one is to install and run a Linux environment, but without having to dual boot or install anything. Everything is pre-installed. Literally, all you have to do is to download a huge file, unzip it, and double-click on one of the files. So I think by this time in cisp310, you'll all be able to do it. It will take longer just because the download is really long. It's a 1.2 gigabyte file. Okay, so that's what's going to take time. All right, so what we'll do is we're going to skip to, this is just a home page of LogicSim, so there's really not much there to see. You want to go there to download the jar file, but other than that, there's not much to do. This is the actual document that talks about adding and subtracting binary numbers. And I think I'm not going to read my own notes here. I just want to show you where to find the notes, okay? I think last time I kind of briefly described the advantages of using binary numbers instead of base 10 numbers, decimal numbers. Did I talk about that? Like your multiplication table got shrunk to 2 by 2, and of the 4 entries, they're all trivial. Okay? So we'll start with that premise here. So instead of reading my own notes, I'm going to use my notepad as my whiteboard, and I still cannot control the font size. I don't know why.
Maybe if you change the font itself instead of the
view.
Yeah.
Okay, under settings, preferences. Okay, it's using the system font, that's why. So it's not taking my selection. All right, I think that's much better. All right, so let's go ahead and take a look at the binary addition first, okay? Binary addition is basically saying, okay, we know how to add numbers in base 10, but how do we add numbers in base 2? Well, let's start with base 10 numbers, okay? Just to remind you how we add numbers in base 10, right? Okay, what is 6 plus 2 in base 10? Well, I'll call it an 8. Okay, let me just leave one more blank line here with a carry of
Zero.
0, okay? So instead of saying there's no carry, we would much rather say there is a carry, except the value of the carry is 0. Is that okay so far? Okay. And by the way, how do you know 6 plus 2 is 8?
6 ones plus 2 ones.
Memorization, okay? When I remember when I was a kid, they would give us blocks. One block would have, 2 unit of length, and then the other block would have 6 units of length. So when you put those 2 blocks together, it becomes 8. But how do you know that is 8, right? Well, it turns out there is another block that has a length of 8. So that's how you know 2 plus 6 is 8. Okay? All right. I know you guys know this stuff already, but that's how we learn and that's how we memorize stuff. Okay, let's try something that's harder. I'm pretty sure you have heard reputations about this class being hard. So this is the harder stuff here. 6 plus, let's make it 7. Okay, that's pretty hard. Okay, so do you still remember what is the result of 6 plus 7?
13.
13, but I would call it a 3 with a carry of 1. Right? Because this is how we can carry out multi-digit addition. Is to look at things not as 13, look at this one not as 13, but a 3 with a carry of 1. Are we still doing okay so far? Okay. But why? Why is there a 3 here and a carry of 1? What about the quantity of 13 that makes this happen?
It's 1 tens place.
Can I represent the quantity of 13 using only one base 10 digit?
No.
Because we only go from 0 to 9. Exactly. Okay, so that's why we have a concept of a carry and basically say this place, this particular digit can no longer handle the value that I want to represent. But since I can kind of assume there's a next digit, I'll just tell the next guy and go like, you know what, I can only represent up to here. You can take care of the other part that I cannot represent. That's the carry. Is that okay so far? Okay. All right. So now we move on to binary numbers. And I'll enumerate all possible cases for binary numbers. Okay, we'll start with the most complex one. What is that?
0.
Okay. But remember, we also want to care about the carry. So it has a carry of 0. 0 plus 0 is 0 with a carry of 0. Okay, very profound. Let's try the next hardest one, which is 1 plus 0. What is the result of 1 plus 0?
1.
It's a 1 with a carry of 0. Okay, well that's case number 2. Case number 3. 0 plus 1 is 1 with a carry of 0. And the last one is 1 plus 1. Whoops. And what would be the result of 1 plus 1 in binary?
0 with a carry.
It will be a 0 with a carry, because in binary we only have, each digit can only choose from which 2 values?
0, 1.
0 or 1. 2 is not one of them, which means, hey, if I cannot represent 2, I'm going to inform the next digit and say, you have to deal with it, okay, because I cannot take care of that value. So the result of this one is a 0 with a carry of 1. Okay, out of these 4 cases, let me just change the zoom a little bit so that we can see the entire table. There we go. Out of this entire table of 4 cases, which one is the only one that is kind of odd, when you're used to just base 10 addition?
The last one.
It's the last one, right? Okay. So you look at this, and then you think about all the stuff that we talked about at the very beginning of this class: transistors, NAND 2 gates, AND gate, OR gate, NOT gate, and so on. I don't see any connections. These are arithmetic operations, addition, adding stuff, right? It's not a logical operation. Is that making any sense? Okay, so there's no connection, there's no continuity from what we talked about at the beginning of this class to base 2 addition. Let's try to bridge that, okay? So let's try to make that connection right now. Okay, what connections are we talking about? Okay, so let's go ahead and take a look at this, but from a different perspective. So this time I'm going to look at this as a table. We have a bit called x, another bit called y. And by the way, y is a bit called a bit. What is an abbreviation of some kind, but what is it? BIT. Why do we call a single digit that can either be a 0 or 1 a bit? BIT. Binary digit, exactly. The B comes from binary and the IT comes from digit. Okay, that's how the word bit came along. So we have x plus y here, and on the third column, I want to represent the carry of x plus y, and the fourth column, I want to represent the actual result of x plus y, which is the 0, 1, 1, and 0 here. Okay. Okay, making this table is not difficult because we just have to go back to all the previous cases. 0 plus 0 has a carry of 0 and a result of 0. Okay. 0 plus 1 has a carry of 0 but a result of 1. Okay. 1 plus 0 has a carry of 0 but a result of 1. The only one that is kind of odd is 1 plus 1 has a carry of 1. But a result of 0. Is that okay?
Yes.
It's just a much more concise way to look at the 4 cases that we have listed earlier. Okay, that's not too bad. Okay, so now this is the trick. Okay, the trick is to look at each column for the carry and the column for the result and say, can I re-express that as a logical expression? That is the question. We'll start with the easy one, the carry. Okay? Can someone think of a logical expression so that if the 2 inputs are both zeros, the end result is a 0? When at least one of the 2 input is a 0, the output is still a 0. The only time the output is a 1 is when both inputs are 1s. Can we find a logical operator that can do that?
And
A regular and, not negated. Right? Just a regular and can do it. Is that making any sense? Because, okay, well, that's kind of useful because now we can say the carry of x plus y is really just the same thing as x, logical and y. So this is the first bridge, okay? This is a bridge going from logical expression to arithmetic operation. Is that okay? What about the result? The result is a little bit tricky because we actually do not have, well, we kind of do, but not. Okay, in C++, which operator would kind of resemble what we want to do here? 0, 0 as input, the output is 0. 0, 1 as input, the output is 1. 1, 0 as input, the output is 1. 1, 1 as input, the output is 0 again. So which operator in C++ do you think kind of resembles this? Exclusive OR would do it, but exclusive OR is a bitwise operator, not a logical operator. So if you are to pick a non-bitwise operator, which one would do this?
Or.
An OR doesn't quite do it. I'll show you this one. It's actually kind of surprising. Not equal to. Now, since x and y can either be a 0 or a 1, don't you think the not equal to is going to do it? Yep. But there's no gate logic. There's no easy gate logic corresponding to not equal to. So let's not use this one. I'm just demonstrating that you can use it as an operator. Okay, so, and I don't want to use the bitwise exclusive OR operator. So what else can I do about this? Can I just use regular not, regular and regular OR to make this happen? What do you think? We can do it by spelling out all the cases when the output is a 1. Okay, so the way to do this is to say not x and y, or x and not y. That will do it. Has everybody, signed off on the row sheet? Alrighty. So now we have something that does not seem to be profound, but it really is profound. Because what we have done is to convert arithmetic logic, arithmetic operation, okay, the result and the carry of a single digit addition into logical operations. Now, how does that connect to transistors?
On and off.
Okay, so for each operator that we are using, the regular conjunction, the regular disjunction, and also the regular negation, we already have a way to translate all of those into NAND 2 gates, right? And from NAND 2 gates, we have a way to implement that using 4 transistors. In other words, we can look at this and go like, we know how to perform all of these operations using just transistors. Now, it's going to be a lot of transistors, okay? But nonetheless, we can do it, okay? The point is, we now have a connection all the way from devices, transistors, vacuum tubes, whatever you want to use, to calculations. Not logical, but arithmetic operations. Are we still doing okay at this point? Sort of, okay? All right. Well, this is useful, but it is not going to be the whole thing because this is what we call a half adder. In other words, it's not really a full adder just yet, okay? So we'll go ahead and perform a few examples of adding 2 binary numbers, and then we'll figure out, how to make it happen using, half adders. Yep, go ahead.
But if your table represents the 4 possible outcomes of addition, why is it called a half adder?
That's a good question. I'll illustrate why using the next few examples. Okay, so we'll go ahead and just use a few binary numbers as examples. Let's try 0101 plus 0011. I think that's a pretty good one. Okay, so let's go ahead and perform this calculation, and you can see, oh, this is kind of odd. How can we have a second row of addition here? This row, this entire row here, and let me just go ahead and fill it in and highlight it. This entire row has to do with carry from a prior digit. So I'm using one entire row just to represent that. Okay. Well, if that row represents carries, what about this row here? This row is only representing the actual result of adding the input, the 2 numbers. So 1 plus 1, the result goes here. The carry goes here. Okay, so let me go very slowly so that you know what we are dealing with here. Well, since this row is all about the carry, what should I put here?
0.
It's a 0 because there are no previous digits. Okay, this is already the least significant digit. So the carry, there's nothing to carry into this particular digit. Okay, that's good. So now we can actually go ahead and go and do the calculation. So for the first or the least significant digit, we will be dealing with 1 plus 1. What is 1 plus 1? What is the result of 1 plus 1?
0.
It's a 0, but it does have a carry of 1. Are we doing okay so far in terms of where I put the result and where I put the carry in this particular format? Okay, all right. Now we have a second addition because now we need to add this 0 to the carry from the previous digit to become the actual result, the final result of this column. What is 0 plus 0?
0.
Then we put a 0 here. Are we starting to understand why the mechanism that we just described earlier is called a half adder? Because it only takes care of 1/2 of adding a column. Okay, let's finish this one, because it will be helpful. Okay, what is 0 plus 1? The result of 0 plus 1.
1.
That's just 1. Does it generate a carry of 1?
No.
No. So we're not going to put anything here if it is a 0 at this point because we have a second chance of actually putting a 1 here. So now we have to take care of this 1, which is the result of adding the 2 input numbers, and this one, which is a carry from the previous digit. What is 1 plus 1?
0.
It is a 0 with a carry. So now we put a 1 over here. We got 2 chances to put a 1 over there, because one chance to put a 1 over here is adding these 2 digits, but the second chance is from adding these 2 digits. And each time we have to come up with a carry and the result, that's a half adder. And that's why in order to finish one column of addition, we need 2 half adders. And that's why it's called a half adder, because the whole thing requires 2 of these. Okay, well, let's go ahead and finish this. 1 plus 0, we put the result here. What is 1 plus 0? 1. Does it have a carry of 1? No. So we don't want to put a 0 here, because if we put a 0 here, it is a confirmation that it has no carry or has a carry of 0. So if we don't know yet, then we'll just leave it empty. 1 plus 1 has a result of 0 and a carry of 1. We put a 1 here. 0 plus 0 is 0 with no carry. 0 plus 1 is a 1 with no carry. Now this carry doesn't seem to be useful at all, because after all, we are only dealing with 4 bits. But this dangling carry is actually important when we design the processor. We'll deal with that later. But we do want to calculate what is the actual carry from the most significant column. Are we doing okay so far with this one? Yep.
How does that logic statement relate to the truth table you brought up there, the not x and y, or x and not y?
That computes the result. So if you plug this 0 into here, you plug this y into here, and you go through this whole expression, the end result will be this bit here. And this works for all 4 rows. Yep.
Because there are 2 chances for the carry, isn't it possible to get each chance to get 1
We
carry?
have to somehow combine the 2, so we'll talk about that too. That's a good observation, that we have 2 chances of setting the carry of the next column. So how do we work with that? So that's a good question. We'll address that. Yep, go ahead. Mickey? No? Oh, okay. I thought you had a question. That's okay. All right. If there's one thing that you guys have learned, for those of you who have taken classes from me prior to this class, what did you learn from me? You always question my answer. Okay? How do we know that really is the right answer, right? I just threw a whole bunch of 0s and 1s onto the whiteboard, right? How do you know it actually makes sense? Now, if you study before the class, then you can kind of cross-check that, okay? But it's always good to double-check using another mean. So what we'll do is to look at 0101 as a base 2 number and say, okay, what is it actually representing in base 10?
5.
It's representing 5 because we have a 1, we have no 2, and we have a 4. Okay, 4 plus 1 is 5. What about the next one?
3.
It's a 3. And what about 1000 in base 10? Yeah, we have 18. So there's no confirmation that it is wrong, because I can do something that is consistently wrong and it will still end up as a false positive, but I'm fairly sure this is done correctly. Okay. Are there any questions at this point? Questions? All right.
Leading zeros are not important at this point. Leading zeros.
Leading zeros are not important at this point, but we do want to represent them. So in other words, in this case, I'm dealing with a 4-bit processor. Okay, every single addition would involve 4 bits. Okay, the first number has 4 bits, the second number has 4 bits, and the result has 4 bits. Any other questions?
And
Okay.
we're going to go over what happens when we have that extra bit at the end, right?
That extra bit is actually quote-unquote stored, but it's not stored as a part of the result. It is stored as an independent dangling flag that we can use later on, for certain instructions. Okay, those are all good questions. Are we ready to move on? Okay, so if we're ready to move on, then we'll go ahead and go like, okay, this time I don't want to deal with actual numbers, okay? So we are just going to say the first number has A, B, C, D as individual bits. So A is 1 bit, it can be 0 or 1, B is another bit, and so on and so forth, okay? And then we have, you know what, this is not a good terminology. We'll use the array notation. So this is A bracket 3, A bracket 2, A bracket 1, and A bracket 0. And the other number is kind of the same thing. So it's kind of an array, and each element is a bit, okay? And we're adding these two numbers. Alrighty. Okay. How do I represent this guy here? So we'll just go ahead and call this sum, okay? I'll just go ahead and finish the whole thing. Okay. And this one is carry, so we have C3, C2, C1. And this one is a constant of 0, so we don't need to use a variable for that. And this is the final result. Okay, so now I'm representing the same thing, except it's in, well, we have one last carry. So we'll go ahead and represent that one here, C4. There you go. Okay, well, that's good enough. Okay, all right. Okay, so if I want to use the R and the C to represent stuff here, what is S bracket 0? That's the result of adding which two bits?
A0, B0.
Exactly. Okay. And R0 in this case is trivial because we're just adding 0 to sum, so this becomes really just that. Okay. So that's kind of like an exception case here. What about S1?
A1 and B1.
The result of adding A1 and B1. Okay. What about C1? Now this time C1 is not trivial because it can be a 0 or a 1. So how do we express C1? It's the carry of.
A1.
Okay,
A1
so
and
now we have to think about it. This brings us back to your question of, hey, we got two ways to set the carry of the next column. How do we combine those two? So we'll go ahead and name the components first, and then we'll say, but how do we look at these components and come up with the actual answer? Okay, what are the components here? The addition of which two bits can affect C1?
A0, B0.
A0, B0 is certainly 1. A0, B0 is 1. And then the other one is kind of trivial in this case, but I'm going to name it anyway. It's the carry of adding S0 with 0. But we know that's going to be a 0, so it's not a main issue in this case. The big question is, how do we combine these two? What operator do I put here to combine the two carries into one? If you put an AND here, that means they both have to be a 1 to set the next carry. It's not an AND, because they cannot both be 1, by the way.
Oh,
You did an OR. This needs to be an OR. Okay? So the other one, okay, let's move on to the next one here. S2 is easy. Okay, that's the result of adding A2 and B2. That's the easy one. What about C2? Go ahead.
What about on C1 if they both, I don't think they can, but if they both.
They cannot both be 1.
Yeah, okay.
Well, C1 in particular cannot happen because the carry of adding anything to 0 is a 0. So we know for sure this component is a 0 to begin with. But if we want to express why and explain why it's a 0, it's because the carry of adding anything to 0 is a 0. So it's not important how we merge the two carries in this case. But C2, on the other hand, is important. So C2, according to the template that we have so far, is the carry of adding A1 and B1 with the disjunction of the carry of adding what?
S1.
S1 and
C1.
C1. That's it. Yep. Given S2, which is the first real general case pattern, can you guys work on S3 and C3?
Yes.
It's pretty easy, right? Because you just change the numbers off by 1. In other words, after the first 2 columns, it becomes pretty easy. C of I, okay, C of I is the result of what?
The carry of A I minus 1.
B I minus 1, or the carry of S
minus 1.
I minus 1.
0.
No, I minus 1.
Oh, I.
Yep, there you go. What about R? Oh, we never I forgot to do one thing. What about R? R1.
R1 is equal to
That's an easy one.
S1 plus C1.
It's R, S1, and C1. Right?
Yep.
Okay. So the carry, the intermediate sum is, that's the easy one because it's just, AI, BI, and the result is what?
SI.
SI minus 1.
SI plus CI.
Yep, SI and CI.
Yeah.
The only time it has to be from the previous column is when you're dealing with the carry. Yep.
So if the carry of AI minus 1 and BI minus 1 is 1, and a carry of SI minus 1 and CI minus 1, they just become one.
They
carry.
cannot both be ones though.
They cannot.
They cannot both be, yeah. Okay, so
Okay, gotcha.
let's think about it. Okay, so what you're talking is, what if this plus this is a carry, and then this one plus this one also makes a carry,
Yeah.
right?
Yeah.
It cannot happen, because if this plus this is making a carry, it automatically means this has to be a 0.
Oh.
And when one component is a 0, doesn't matter what the other one is, it cannot have a carry.
Okay.
So that's why you cannot have the disjunction cannot have ones on both sides.
Okay. Makes
For
sense.
sure.
Makes sense.
Yeah. Does everybody kind of understand that part? That's a very good question. Okay, in other words, how do we know that only one, at the most, one of these two is a 1? They cannot both be 1. The answer is, if, okay, I'm getting back to this one here. If S1 is a 1, doesn't that tell you something about A1 and B1?
If it's one of them is a 0.
They're both 1s, right? That's how you can make the carry to become a 1.
Yeah.
But if A1 and B1 are both 1s, in order to make this carry 1, to make the first part of the equation a 1,
That's what.
that makes S1 a 0. If S1 is a 0, then it doesn't even matter what C1 is. Though the addition of those two cannot give you another carry. So that means when you're dealing with the expression of CI, we know for sure that only up to one of the two sides can be a 1. They cannot both be 1s. So that's a very good question, and I hope the answer is sufficient. Basically to prove that it's not possible. All right. So are we still doing okay so far? Now, yeah, go ahead.
Is there a significance of you using arrays for this example?
Yes, there is a significance of why I'm using an array, because how do you think people design processors? Okay, so let's say you're working for Intel as a computer engineer. Okay, because computer engineers help design processors. Okay, so how do you think people design processors? Do you think they work with Logisim type of software to design a complex processor like an i5 or an i7? Why not? Why not use a graphical tool? Because it's so intuitive. It's the same reason why you learn to program in C++, but not in Scratch. Graphical programming has one major, well, I wouldn't call it a flaw, but it has one major characteristics that makes it difficult to use for large-scale projects. Why?
Limited.
Hmm?
Limited.
Well, it's limited in a way, but what happens when you need to insert something into a big picture? You need to move all the other stuff around, right?
Mhm.
And that makes it very difficult to use when you're designing something that's really, really complex. Go ahead.
But I answered it.
Okay, thanks. All right, so, okay, now we get back to the design of i5, i7 processors. So here's something that's complex. So if a graphical tool cannot be used, then how do you express how the individual pins or components inside the processor relate to each other? Expressions, equations, okay? In fact, the programming language that they use to describe logic inside the processor is called Verilog. Verilog. And can anyone guess which programming language it resembles?
Assembly?
No, it's high level, so it's not assembly. Something that you have learned already,
C?
or should have learned already. C++. Yep, Verilog has a syntax that is very similar to C++, except you're not specifying a program. You're not specifying the steps of how to get something done. You are specifying how components inside a processor or some other thing that makes out of logic gates, and you're specifying how the gates should be connected, just like what we're doing here. Okay? Okay, fine. If you look at C, S, and R, and AB, they all handle just one single column, right? Okay? Because A, B, C, S, R are basically 5 components of one column. If you're designing a 64-bit processor, doesn't that make this really kind of complex and really kind of long? No, you just make a loop. In Verilog, you can actually make a loop and say, oh, I just need to replicate this whole thing a few times. So you just say, for int I equals 0, I is less than 64 plus plus I, and stick all of this stuff here inside the loop. Well, proper syntax, semicolon, semicolon, indentation, and we don't go from 1 because 1 and 2 are kind of special cases. So I think we can go from 2 because the first 2 columns are a little bit special. But starting from column 2, all the way up to column 63, it's all the same stuff. That's Verilog. Okay, so Verilog is a quote-unquote programming language, but it's not really programming per se. It is a language to express the design of logic gates. And it has functions and stuff like that. So once you know how to make something that's big, like R and C and R as functions here, you can actually call quote-unquote functions because now it becomes a macro to put in the necessary gates to implement it. Yep,
And does it compile to the machine language right after?
No, it does. It does not compile to machine language. What it does compile to is an internal representation of how the gates are related to each other, which is not at a silicon level. Okay, from the gate description to silicon level, at least in 98 or so, that particular technology is kind of like a black art, because it's difficult to, it's very proprietary. Okay, that's one piece of software that Intel probably would guard, very, with its life. Because how you go from logic gates to actual transistors, that's a really important piece.
Secret?
It's it's not only secretive, it's also a black art. In other words, the science or the engineering of doing that is still kind of, there's a lot of stuff that's like, let's turn on this flag and see what happens kind of thing. It's not optimized. The optimization part is really difficult to do.
Wow.
Yep, but those are good questions. So if you want to, for those of you who are interested in this stuff, you can look up Verilog, and Wikipedia has a really good description on it. It's a HDL, or a hardware description language. That's basically a whole category of languages. Okay. Are there any questions at this point? no questions, we'll go back to the slides a little bit. In fact, I'm just going to go back to Logic Sim here, and we'll go ahead and make these circuits. Okay, so we'll go ahead and make a half adder circuit. Now in Logic Sim, what you can do is you can go to project. Let me see, edit file. Can't remember which button to push to make this happen. Add circuit. And we'll call this a half adder, okay, HA. And you can see now I have my main and I have my sub-circuit called a half adder. Okay, so we'll go ahead and implement a half adder. How many inputs do we have for each half adder? No, that would make a full adder. Half adder, 2. Okay, very good. So each half adder has 2 inputs. The squares are input pins. So we'll need 2 of these. And you can label these 2 if you want to. So I can label the first one A, and label the second one B. Okay, here we go. And how many output pins do we have coming out of a half adder? There's the result and there's the carry. Okay, 2 outputs. So now we'll go ahead and pick up these two of these. Okay, so that's 1. Label this one as our result. And we'll pick up another one and label this one as our carry. Okay. How do we connect these things? Let's deal with the easy one first. Which one is the easier one? The carry is the easy one, right? The carry is a logical AND. So that's a pretty easy one to do. So let's do that first. A logical AND is this guy here. You can just go ahead and pick it. And we'll go ahead and make it a smaller with only 2 input, okay? Because that's all we need. We don't want something that's too big, and we don't need it like that. So we'll go ahead and drag the lines over here. One of the input is from A, so we'll feed A into one of the inputs. We'll feed B into the other input. And we are done. Okay, that's carry. The result, depending on whether you want to use exclusive OR as a gate, if you use the exclusive OR gate, it's easy. That's just one gate. If you want to implement it using AND or just not, that becomes a little bit more difficult. Okay, but we'll go ahead and take a look at how to do that.
3 NANDs. 3 NANDs.
Sorry?
3 NANDs.
You can do it that way too, but I'll just go ahead and implement it the same way as I wrote on the other side. So the final output is the output of an OR gate. So we go to gates here, and we specify OR gate, change it from 5 to 2 input, and make it a narrow one. And we'll just put it here. But what feeds into the OR gate? Each one is coming from an AND gate. Okay, let me just go back to the equation first, just so that you get reminded of the equations. Okay, so what we're trying to do is this logic here. You can see the final output, the last operation is an OR, but each component of the OR is the result of an AND. So now we'll go ahead and pick up 2 AND gates. And now just go ahead and replicate this one so we don't have to, no, don't do that. Back. There we go. So we'll take this one and put it here. You can also select a whole bunch of stuff and just move the entire thing up and down. Okay. All right. So we're taking the output of these 2 AND gates and feeding it into the input of the OR gate. Oh, it's not symmetric. All right. Close enough. Okay, now is the difficult part because we have to negate A to put it into the first one, but B has to be non-negated to go into the first one. For the second one, A is non-negated and B is negated. Okay, I can use a NOT gate to do that, but it's really a lot of trouble. So I'm going to cheat because with any type of gates, okay, and or and whatnot, you can actually specify whether you want to negate 1 or 2, or you can specify which one to negate. So with this one, I'm going to specify the top one to be negated. You can see a new bubble here. That bubble is a negation symbol. Okay, and for the second one, I'm going to do the bottom one. So I'm not going to negate the bottom one. Then all I have to do is to draw the lines to make the actual connections. So A goes to the top one, A goes to the top one, B goes to the bottom one, and B goes to the bottom one. Now we have a half adder. And what do you think? What do you do? When tech says, here's the solution, I just solved the problem, what do?
You test it.
You question it, right? You say, really? Okay. So we'll go ahead and test it. There are only 4 possible cases, so that's pretty easy to test. 0 plus 0 has a result of 0 and a carry of 0. Does that make any sense?
Yes.
Okay. 1 plus 0 has a result of 1 and a carry of 0.
Yes.
1 plus 1 has a result of 0 but a carry of 1.
Yes.
0 plus 1 has a result of 1 but a carry of 0.
Yes.
We have just tested all 4 cases. They all work. Are we doing okay so far? Now we want to make a full adder, okay, out of the half adders. You might think, oh man, we're going to have to replicate this whole thing. You know, it's going to look complicated. Well, that's not actually the case, because what we can do is we can turn it into a quote-unquote subroutine. You can right-click on this one, and let's see. You can edit the appearance. Well, this looks okay, you know, to me. I'm just going to zoom in a little bit here. We might want to do some labels though. So I'm just going to label these pins a little bit. The top one is A. For addition, it's not really that important because it's commutative. You can swap the order. But for subtraction, it is important. The other one is R. And this one is C, which is a carry. And you can also, you know, reposition things a little bit just to make it look nicer. So cool. I will fail as an artist, but you know, this is close enough for our purposes. All right. So now we want to implement a full adder, okay, out of the half adders. This is nice. This is a subroutine. Okay. From here on, we can just look at a HA as a component. We don't have to look at the details of a component, you know, inside of the components inside the half adder anymore. Okay, so now we go ahead and go to here and say add. No, we want to add a new circuit, and this time it's a full adder. So I'll just call it a FA. And now we can design this new full adder out of what? Half adders. Very good. So what we'll do is we'll drag. I can't remember which button I'm supposed to press. There we go. So when you click on this one, it becomes a selection. So we'll need 2 of these. So we'll go ahead and pick up another one and stash it. Let's see. Here's good. Okay, there we go. All right. Now, with a full adder, we have 2 inputs, right? The 2 bits that we are supposed to add for this column. But we have a third input too. Who's the third input?
Carry.
The carry from the previous digit. Okay. All right. So we'll go ahead and handle all the input pins first. So here's the input pin of the first number. Here's the input pin of the second number. And here's the input pin corresponding to the carry from the previous digit. What about the output of a full adder? How many pins do we have as the result or the output of a full adder? The result of the entire column and the carry to the next column. Okay, very good. Two outputs. So we have one output here, we'll stash it over here, and then we have another output, we'll stash it over here. And it doesn't hurt to label these things, so we'll go ahead and label this one as input A or input in A. This is in B. This is carry in. This is the result of the entire thing, so this is the result And this is carry out, C out. Go. All right. So we kind of know how to connect to the first one. That's an easy one. We just take the input pins and stick it to the first half adder. That's the easy part. Now we have to figure out what do we do with the second one. What do you think? We take the result of the first half adder, and that becomes one of the inputs to the second half adder. And then we take the carry bit from the previous column and feed it into the other input of the second half adder. Is that making any sense? Well, let's check the equations, okay? Because the equations actually should tell us how to do this. So we'll take a look at the equations. The carry output of 2 is, well, it's a disjunction. We have just handled the individual one. So we need a disjunction. We need an OR gate. So let's go ahead and put an OR gate, and you guys can tell me how to hook up the OR gate. So we'll do an OR gate here. Change the number of pins to 2. Make it a narrow one. All right. We have some loose connections here. Okay. How do we deal with the loose connections? We have 3 outputs, a disjunction, and 2 actual pins as outputs. How do we make all these connections? The result of the second half adder, where does it go? It's the result of the entire full adder. So that just goes to the R pin here. Very good. And we have a carry out here. Where do you think this pin should connect to? To the output of the OR gate. Very good. And then what will go to, well, this is kind of trivial, but what should go into the inputs of the OR gate?
Both carries.
Yep, exactly. It doesn't matter which one because disjunction is commutative. So the order is not important in this case. Now we have a full adder. Out of a full adder, this is one single column. Okay, you can handle the addition of one single column. What do I do when I want to have a 4-bit adder? We stack up 4 of these things, right?
Yeah.
So we can now use this as a component. Okay, we can say edit circuit appearance, and in main, I can now actually use it. So, and when I'm in the main circuit, I can now say, give me a full adder, give me another full adder, and so on. So now it's just a matter of connecting the full adders to give us a multi-digit adder. All right. So I'm going to have to leave here, stop here for the lecture, and then for the lab portion, I'll show you guys how to run Linux using a virtual machine. So that's kind of important down the road a little bit. And let me just turn off the recorder.